Okay, so talking about optimizing gradually typed programs. First note, just speed matters, both developer speed. People want to go fast. They want to develop their applications as quickly as possible. They don't want to be slowed down unnecessarily. And secondly, they also want fast programs. Nobody wants a slow program for anything unless you're doing something kind of obscure. Ideally, the faster the better, as long as it's easy to develop. So I'll get to why this is kind of I think, a blocker for certain things. But yeah, gradual typing, unfortunately, can have some performance issues. First, a little bit about it. So there's this kind of notion of like a couple of things that I think are really critical to gradual typing. One's the obvious thing, which is that you can mix static and dynamic typing within a single application. And secondly, that you can gradually actually start changing and adding types. So in this example here, there's micro-level gradual typing where we had this kind of simple successor function and we annotated it to say that it takes in integers and returns an integer. And that's the only type annotation someone may want to add, to start with and just check that they're doing the right thing. In other languages, they do it more at the module level. But either way, you gradually either add types to modules or you gradually add types to functions within a module. The other thing about gradual typing versus optional typing is soundness. So you don't want to have annotations be completely erased and then have your type annotations not be kind of honored at runtime when dynamic values sneak into your kind of statically typed regions from your annotations. One thing related to performance, though, is that if you have kind of completely statically typed regions, there shouldn't be any runtime type checks on your values. So for this successor function, it was completely statically typed. You shouldn't have any unnecessary casts that are going on. However, when you're in your F1 function over here and you're kind of passing a dynamically typed value into the statically typed context, you have these casts that are inserted, which are just runtime type checks generally. And they usually have an associated blame label to kind of say where the problem is going on. You could think of that as like source location information or something else about your program. And so in this context, if something goes wrong, then you want to blame the kind of correct location and kind of say where your dynamic code caused issues when interacting with your static code. These runtime type checks don't come for free, and so you can get performance penalties, which I'll get into. First, I want to talk about a little bit of a case study that I personally experienced recently. So I transitioned into working on quantum compilers and inherited this quantum compilation code base that was completely written in untyped Python. And I was like, hey, it'd be cool if I could add some annotations. There's these different modules. That was a parser, kind of gate rebaser, ion transport, optimization routines, and code generation. And a test suite, and this is what I wanted to kind of really get to, that takes hours to finish, that's verifying certain things about transporting different amounts of ions around. We eventually were like, well, it would be nice if our builds and our continuous integration had more static type checking, so why not gradually migrate with MyPy? So this is an optional type system. It doesn't have soundness, but you still wanted some of that kind of static routines. And so, I could have thought about going and kind of typing a module at a time, either typing my parser and leaving my code gen and other things untyped, or typing the code gen and leaving other modules untyped until I kind of get to this top region where I've added types to everything. However, what could have ended up happening if we were dealing with soundness is that certain modules could have added, when you added those types, could have incurred a lot of runtime type checks that really slowed down your program in certain regions, and they might have had okay performance in other regions. And then finally, this would be hard to do all at once, once it was completely statically typed, if we were using soundness, you would have a fast program. And this would be a real problem to get into these roadblocks because, like I said, our test suite is taking hours to complete. if all of a sudden we're getting, 3 times more kind of slowdown, we're looking at half a day. If I get 10 times or more slowdown, I'm looking at an entire day, and that's really going to slow down developer progress, and it would just personally be really annoying for us to actually get kind of code developed and integrated while doing this. So yeah, like soundness is great. However, slowdowns for certain things could be kind of intolerable, even at just a few kind of multiplication factors. So yeah, I want to avoid casts as much as possible, right? So it's nice if you can still gradually annotate things and mix static and dynamic, but not have unnecessary casts kind of incurred in the execution of your program. One way that you could think about doing this, and a few approaches I've thought about previously, is to infer types. The way that this one kind of varies our approach is that we're going to infer types for functions, and then we're going to do type specialization based on that, and basically duplicate your functions and kind of use these fast versions internally when you have statically typed arguments, and otherwise, use your dynamically typed version. And this can be combined with like other approaches to optimizations, like using a JIT, which will do that kind of on the fly. Based on dynamic information. And it can also be kind of used with approaches that look at your cast inserted program and also try to do analysis to take away casts. So it's orthogonal to a lot of different optimization approaches you could think about. And one thing we really wanted was that optimized programs still need to blame the same. So like you don't want a freaking semantics changing thing for your program, right? Like you want the same value if it evaluates, and you don't want it to all of a sudden blame something else just because some optimization, started adding type information somewhere. And so we can do this while still using these fast versions of this program. So this program on the left, there's this kind of bottom call to F2 that fails. Let's see if I can highlight that. Over here, because it's passing an integer into this function, and then it eventually gets dynamically checked against Boolean. So that should fail and it should blame. Why? So when you're optimizing, you still want the same behavior. So when we're using these fast kind of inferred functions in the code generation and switching calls to them under the hood, we'll see that like you're eliminating some casts that were here on the left by calling these fast versions. However, the same cast is still appearing right here. And so you'll eventually kind of step and execute until you blame that ly cast. And I guess most of the time you may not care that you get to your failure condition that much faster, but it is really important for your programs that succeed. And I don't think there's anything wrong with getting to your errors faster. It improves development speed. So yeah. The way that we're going to do this kind of hinges on subtyping to kind of keep things safe, which I'll get into later. But basically, we use subtyping judgments, which can't fail if you're casting from a subtype to a supertype. So yeah, the approach that we use is called discriminative typing. It uses my previous work that I kind of worked on with Sheng on migrational typing. So that's this kind of type inference approach to look at this kind of space of possible typings. The second thing we do is pick a maximally typed migration for each function and use those to kind of generate your specialized kind of fast versions. And then finally, we use a cast insertion procedure that uses subtyping judgments for safety. There's the subtyping constraint solving. So the first part of this is typing this region. So it may be the case that you've already partially migrated your program. So you're starting over here in this blue region. And then you're going to basically want to get to the more static regions so that you're having static code interacting and not doing runtime type checks. Unfortunately, because you're dealing with a gradually typed language, there's usually either some dynamic features of that language that cause trouble, or just inherently, like you can do things that may make it very difficult to kind of infer static types for everything. So you could get to the situation where you have more than one possible set of maximal kind of migrations of types. We don't have any particular one to kind of say, which is the favorite, but we just kind of pick one and use those. So to kind of illustrate a little bit of this dynamic idiom stuff causing trouble, here we have a program that has a parameter that's obviously an int or a string, and another one that's a suffix that's kind of always a string. So it's perfectly fine to kind of type suffix with string, but trying to say enter string is just an int or just a string causes trouble. So you need some calculus with some kind of union type or something else. But if it doesn't have that, then you kind of have to leave it dynamic. So we're not going to consider union types. So in this case, the only things that you can do to enter string are leave it dynamic and then kind of try to maximally migrate towards your suffix parameter having type string. So this is the best kind of case that you can have. You can't fully infer types for this. Again, you need union types or something else. So we can consider all of these different typings at once with this technique called variational typing. It uses these variational types, which are kind of an interesting combination of like product type, and sometimes it acts like a union. It's a little interesting, but one of the things to note is that we have unique names for these types. So there's this choice name A that's going to be uniquely associated with this enter string parameter. And then there's going to be choice name B that's kind of uniquely associated with a suffix. And then we're going to have these additional things to kind of talk about the typing of this program. So the green tops represent this program will have a type checking success. The red bottom represents that it will have a type checking failure. And basically we can see that you can do whatever you want to suffix, but enter string has to be left with the dynamic type. If you try and move it to using type int or something like that, according to this over here, then you're going to get a null typed program. So it's not a valid migration. So we use that to kind of infer this like spectrum of different possible typings for your program. Then we go and we're just going to kind of arbitrarily, start picking migrations for all of these different functions. So what really kind of drives the meat of this is this variational cast insertion procedure, where you basically kind of get your type, your original type that somebody provided over here in a choice, and then you get this fast version type that we could find from that previous migration process. And then at different function application areas, you kind of say, hey, what choices do I have for the function that's currently being called? If the fast version, if all of its arguments are subtypes, then we're safe to go ahead and use the fast version, and otherwise we'll use the slow version. So there's a lot more going on with some subtleties in here, but that's the heart of it, is the use of subtyping, kind of constraint solving for this variational cast insertion process to make sure that we're only calling these specialized functions with arguments that won't cause blame errors. That will be new. And then we kind of evaluated this on reticulated Python and a bit on Grift. And we found that for guarded reticulated Python, we got speed up on most programs. And these are looking at basically, for certain programs, the entire kind of lattice configuration space of different typings. They're all relatively simple programs, but some of them have too large of a space to completely sample, so we would just randomly pick different typings. And then, yeah, we found most programs got some amount of speed up, with some getting really noticeable speed ups. We did get slowdowns, unfortunately, on certain programs, which is not great. However, it's not too bad given that it's a small number of configurations that are hitting this. So to conclude, this discriminative typing could speed up many programs. The program semantics don't change, so it always blames the same. It always returns the same value, either tagged or kind of untagged. You only have an O of n increase in program size. I think it's a relatively simple combination of inference, specialization, and gradual subtyping use and kind of some constraint solving procedures. However, there are some threats, I think, to its use in generality. It works best in kind of simple functional languages with more rigid structure, and most gradually typed languages in practice are not that. And yeah, so extending the inference would be difficult. And then finally, there are pathological examples that can cause exponential blowups in compile time. However, in practice, at worst, I think we saw more like an order of magnitude slower, and usually just a couple 2 to 5 times slower for compilation time. But yeah, that's it. Thanks.
Okay, questions?
Yes, I saw you had this inference that you tried to take the few types that were added and sort of added them to more places. And at the same time, it seemed that you described the dynamic typing thing as you had a process of trying to add more and more as a human, which means it would be very nice if you got feedback about exactly which were those places where it inferred things. Does the system give any help with that?
No, this is under the hood. So it's some previous work that suggested migrations that would improve performance. So those were more clear about how your program was changing. This was intended to be, a semantics preserving optimization under the hood. But yeah, it doesn't actually say anything about how the migration changed things.
I have two questions. One is a simple one. If you duplicate a lot of functions, we noticed back at the rise already that you get register pressure. Did you experience anything like this?
That could explain some of the slowdowns as well. I think most of them were related to, there were certain cases where higher order casts would create proxies and that would slow things down, even though it was like simple checks. But no, I didn't actually get down to that level of evaluating register pressure.
So the second question is more interesting in the sense, in particular, Python's type system is very impoverished.
Yeah.
Xena, for example, try to add union types. When you have union types, you experience what we experienced in type bracket, that surface programmers use union types to make very, very precise types, the maximal types, right? And then we have benchmarks where the performance just goes way down. So I don't think we have to take your results with a grain of salt in the spirit of when you add real interesting types, like TypeScript level types to articulate it, it won't work. That's my guess. I mean, it's not a question, it's more a statement, but you can please react.
I was going to say, I would agree with that. So we kept to a core small calculus just to evaluate whether this had any merit. But yeah, I think once you get to, set theoretic types or more complicated things, like if you're trying to do like partial object inference, you're going to create proxies that are going to create a lot of slowdown. So it's tough. I will say though, there are certain things that you can do. I have this bonus slide. So if you have a program where you're like doing something like using plus in Python, which again is heavily overloaded to work with different things, you could still do an unsound kind of inference of integer types and use that as your specialization. And if you have a hot loop, you can still call that version and avoid like a more generic object cast that's like looking for underscore add. And then still use the slow dynamic version, like if you use plus to concatenate two strings or to work with different objects. But yeah, I think the more and more you push things, you could probably run into complicated proxies that are inferred and wouldn't help. So yeah.
Okay, let's thank our speaker.